Is going through some examples on momentum. So this is the latest version. It'll be on Blackboard tonight at midnight, but it's on the board here for you right now, just so you know what's due when. This is set number 10, number 11, number 12. We're done. Okay. These are the last 3 homework sets to be turned in for grade. Okay. It goes all the way through chapter 6, but not chapter 8. There'll be at least one problem on the final on chapter 8, but you won't be responsible for turning homework in on chapter 8 at the end of the quarter. Okay. These are continuity. These are momentum plus 2 energy. And these are all energy and about 3 problems or 4 out of chapter 6. Okay. Now, we're passing back homework there. And we'll go over that a little bit later. All right, there's the equation that we had derived from the Reynolds transport theorem involving momentum. Just to go through it again, the left-hand side is the summation of all the forces that act on the control surface that we're looking at. The right-hand side, the first term, is the time rate of change of momentum inside the control volume. Steady state, that term goes to 0. The second term, if it's uniform velocity profiles, we'll use the summation. Sum over the control surface, and this is the momentum into and out of the control surface. Okay, and I put down there, just to start with a little example, a simple example, where we have maybe a large diameter pipe at the left-hand side, and there is a nozzle where the diameter becomes smaller, and then the fluid exits the smaller nozzle area out into the atmosphere. The pressure on the left-hand side is, of course, different. It's in a pipe. Okay, so we can write various things about that particular situation. First thing we do is we show a coordinate system. Which way are we going to consider positive and negative? So there it is, to the right and up. We're going to analyze this. Let's start off and look at continuity. Okay, continuity, if we show our control surface and control volume, we label that control surface. What's inside is the control volume. Now we have to put numbers on it. What do you call 1, 2, 3, 4, or 5? Okay, I'll call what comes in 1. So this is location 1. So this is P1, V1. This is location 2. So this is P2, V2. Of course, it exits to atmosphere, so gauge pressure, atmosphere is 0. Okay. All right. Continuity. First of all, we say that it's steady state. So nothing varies with time. So then we know continuity. It says the mass flow rate that comes in equal the mass flow rate that goes out. And then we're going to say that the density doesn't change. It's called incompressible. Okay, if it's, so this is true if steady state, SS steady state. And then we have Q1 equal Q2 if incompressible. Now, of course, the areas are different, so we don't want to say, obviously, that V1 equal V2, because A1 is not equal to A2, so we can't say the velocities are the same. So that's where we end up with continuity, in particular, two assumptions, steady state, incompressible. If we want, we can write Bernoulli's. One, two, two. Notice that the elevation Z is the same, and so we have P1 over gamma, V1 squared, P2 over gamma, V2 squared over 2G. And we already said that P2 was 0, so we'll just go ahead and do that. So there's Bernoulli 1 to 2. To apply Bernoulli's, though, you have to say, are we neglecting friction? Yes, we'll say we are. So it's inviscid. Inviscid means neglect friction, so it's frictionless. So if you hear the word frictionless or inviscid, it means the same thing in our case. You have to apply Bernoulli's along the streamline. Okay. We will from point 1 right here to point 2 right here. And now we have momentum, the new one. Okay, well, there's the equation right there. I'll just go from here. First of all, we've already said up here, steady state. Okay, steady state, this term gone. Summation of the forces. Obviously, there's a pressure P1 on the left. There's a pressure force on the left. That's P1A1. Which way is it acting? In the positive X direction, so plus P1A1. We're going to assume there's a restraining force required to hold this in place. Otherwise, it would move. So we'll call the restraining force F. We'll show it to the left, because I think that's the way it's got to act. If you don't know, just assume something. If you get a negative sign, when you're done, you guessed wrong. Okay, so F is to the left, so it's negative minus F. That's all the forces on there, because the pressure force on the right is 0, P2 is 0. Okay, now comes the left-hand side of the equation. It says, go around the control surface until you see the place where fluid crosses the boundary. Where it crosses the boundary, do what it says. Okay, so I can start down here at the lower left-hand corner. I go up along the dash line. Uh-oh, stop. Fluid's crossing the boundary. Yeah, it is. Okay, do what it says. Take rho outside of there. So we'll put rho out here. And then V, okay, V is V1, which way is it point? To the right. Now it says, take V dot A there. V is to the right, the V vector. Area vector is to the left. The dot product is minus cosine 180, minus 1. So minus B1, A1. Keep going around the control surface. The top, no fluid crosses, no fluid crosses. Stop here and go down. Yes, fluid crosses. Okay, do what it says. Rho, it's the same rho because it says right here, incompressible. I don't need to put subscripts on row. Row 1 equal row 2. Okay, take the velocity there. Okay, it's to the right, positive, the value, V2. Okay, then I have the last term, this is to the right. V dot A, both vectors point to the right. The angle between them, 0, the cosine 0 is plus 1, so plus V2A2. So make sure you get those signs right. Here's the deal again. When you've got this velocity vector, it can be plus or minus. When you've got the V dot A, this can be plus or minus. Make sure you always check both of those signs. Solve for F. Normally you're given the pressure up here, P1. Normally you're given the areas, A1 and A2. And if you want to simplify it, rho V1 A1 is m dot at 1, and rho V2 A2 is m dot at 2. So that makes life easier sometimes if you know m dot. You could replace rho AB with m dot. And then you've got V2 minus V1 here. M dot, is it m dot the same? Yeah, look up here. Continuity, m dot's the same. If m dot's the same, pull m dot outside, multiply it by the quantity of V2 minus V1. So again, what I'm saying here, if somebody gives you P1, V1, how are you going to get V2 for Bernoulli's? How do you know they're the same? M.1 and M.2. Continuity. Use both of these guys to solve this guy. They build on each other. Okay, check your units. In SI, it'll be pretty straightforward. In English engineering, or British gravitational, not always so straightforward. So watch your units on these guys. This is density, okay? Slugs per cubic foot. This guy's in pounds, okay? So be careful of your units. All right, let's take a look at a similar example, but with some numbers in it. This is a nozzle attached to a fire hose. So here's the fire hose. Looks similar. Comes in here, goes out here. And let's see what we're given here. We're given that the pressure is 2,000 kPa. We're given that the area, the diameter at location 1 is 9 centimeters. Diameter at location 2 is 3 centimeters. So here's A1, here's A2. V2, V1. P2, 0, fire hose. What forces need to hold the nozzle in place? So find F. It's just like my example over there. Okay. Let's, let's see, we got the pressure, right. Mm-hmm. Let's do Bernoulli's first, Bernoulli. Okay, Bernoulli. V1 squared over 2G, P1 over gamma. continuity. A1 V1 equal A2 V2. Solve this guy for V2. Put that V2 over here, step one, put that V2 over here, and then solve this guy. Solve for V1. So from continuity, solve for V2. Put V2 into Bernoulli's in terms of V1. A1 over A2 is 9 divided by 3 squared. Okay, that's 3 squared, it's 9. 9. V2 is 9 times V1. Put that guy over here. Solve him then for, yeah, I know P1. There. I know gamma, it's water, it's a fire hose. I know gamma, 9800. Solve for V1. Okay, V1 7.07 meters per second. You want to get V2 right here, 9 times V1. All right, let's see if I can fit this in here. I need more space. I'll put it over here.
Question. We're finding F, but where is F on this?
Does the guy holding a fire hose, fireman, does he push this way when he fighting a fire, or does he pull this way? That's where the force is.
Okay.
It's the fireman holding the hose in his hand. He has to either push on it or he pulls it back. Okay, if we don't know, we guess the direction. If we have some intuition, yeah. In this case right here, I haven't put it, okay? Same way as over there. Okay, I'm going to put this right up here now. P1A1. Area, pi r squared, 4.5 centimeters squared. That's him, minus F equal. Okay, let's go ahead and put these guys in here. M dot V2 minus V1. Oh, it's right here. M dot times V2 minus V1, which I mentioned just about 5 minutes ago. Okay, that came from here. M dot, we're not given M dot, but we know the velocity. M dot rho AV V2 minus V1. That A times V right there, I don't care what, just be consistent. It's either A1 V1 or A2 V2. They're the same because it says it right here. A1 V1 equal A2 V2. Doesn't matter. Let's see what I took. I think I took times 8 times 57. I took, okay. So this is 1 and 1, I think it is, yeah. Okay. I'll just put this in here right now. The density, 1,000. I think I had A1 right there. There's A1 right there. 5.045 squared. V2, 9 times that guy. So he would 63.6. So we have V2 63.6 minus 7.07. Solve this whole thing for F. 10,180 newtons. 10.2 kilonewtons. So again, we have to use Bernoulli's continuity besides momentum. All right, let's try a little different one now. We'll keep the equation on there, I think. Don't need that one.
Professor?
Mm-hmm.
When you have row A1, V1, where did the V1 go?
Which one now?
Oh,
Yeah, thanks. It's still in there. Was it 7.07? A1, thanks. Good. The answer's the same. Yeah.
I'm a little confused about the mass flow. So you
Yeah.
took it out initially and then used the
Yeah,
velocity.
yeah, I put this guy here. I'm gonna erase this. Equal m dot 1 v1 minus sign plus m dot 2 v2. Then I said m dot 1 equal m dot 2, so m dot v2 minus v1.
Okay, and because you took it out, it's the initial velocity that you used for the mass flow, right?
Which one now?
No, so for the actual equation, or so for where you're solving it out,
That one?
on the top, or like, right,
That
or under that, where you're plugging all the numbers?
Here.
Yeah, so like you use the initial velocity for that, right?
No. Is 1,000 times pi 0.015 squared times the velocity 63.6 times v2 63.6 minus v1. Same answer. It doesn't make any difference if I take A1, there's A1 V1, divided, here's A2 V2.
Okay, so we're,
A1 V1 equal A2 V2. It makes no difference which one you choose. Okay. Now there's a problem, a couple problems from homework probably. These are called turning vanes. They turn the fluid through some angle. So here is a fluid being turned 45 degrees from horizontal. Okay, the flow comes in here and the fluid is turned like this. Fluid flows out here, comes in here. This is the turning vane. This is P atmosphere. This is being held by some kind of a bracket here. To hold this in place requires a force F. So I'll assume that's the force F. This now is the fluid. The fluid water, whatever it is, oil. I'll draw my control volume. The problem's going to say find the force F, of course. Find the force F. All right, I'm going to draw my control volume. That's my control surface. Here's my control volume, the water and the vane. Go to chapter 5. In chapter 5, he's going, there's a turning vane problem right there that I'm going through here. then if you go over to page 218, here's a set of guidelines. It says, several important generalities about the application of the linear momentum equation are apparent in the example just considered. And I'll read one to three, but read them all. There's 9 given here. They're hints about how to work the problems correctly. They're good hints. Number 5. If the control surface is selected so that it is perpendicular to the flow where the fluid enters or leaves, it makes things a lot easier. So what you do is where I draw my dashed line, I guess what I don't do, I could do it, but it makes it more difficult. I can say, you know what, why did you put the line like that? Why didn't you just put the line like that, and like that, and like that, and like that? I could have. But you know what? If I make the line like I drew it originally, which is perpendicular to the place where the fluid is leaving, guess which way the area vector points out? If I do it this way, oh, I could do it that way, but why? Why? There's velocity v, there's the area vector a. I don't want to do it like that. I want both those vectors to be in the same direction, collinear. So I make my control surface, which is my choice, just like a control volume in fluid in statics, it'd be 214. It's your choice. What free body you draw. Some are easy, some make the problem really difficult. The same way here. Some control surfaces make the problem easier, and some make them more difficult. So I choose this dashed line perpendicular to where the fluid leaves and where the fluid enters, because then the vectors are collinear. And there's a lot more hints in there, so I'm not going to go through them all. I do some as I'm working the problem, but yeah, look at those hints, because they can make life a lot easier for you. Okay, now let's see what else we know here. That's 45 degrees. That's water. I'm not going to go through numbers anyway. Don't forget, you always want to put a coordinate system here. I want to know which way is positive. Momentum's there. I had Bernoulli's there, which I just erased, I guess. Okay, I'm going to write down this guy here, the momentum. Momentum. Okay, number 1 now. Okay. Here's the turning vane. Looks like this, okay? Looks like that. Here it is. A water jet comes in here, strikes the vane, and the water jet goes out that way. That's how turbine blades work. That's how a lot of pump blades work. They turn the fluid. Okay, so what I'm going to do then is I'm going to just write that I know that if this is P atmosphere, 0 gauge, the pressure at 1 is 0. I'm not told this. You've got to figure it out. And I know over here that P2 is 0. Okay, good. I know it's steady state. I'm going to assume it's incompressible. I'm going to neglect friction. I can apply Bernoulli's along a streamline. Okay, if I apply Bernoulli's, I didn't tell you, the change in elevation, they say usually is negligible. If they say that, or if they say this turning vane is on a horizontal plane, like this. The water comes in, hits here, goes out there. Is there any change in Z? No. If they say the change in elevation is negligible, is there any change in Z? No. Do the Z's cancel out? Yes, they do. Is P1 equal to P2 equals 0? Yes, they are. What does Bernoulli's then tell you about the velocity? It tells you that V1 equal V2. Okay, so now we know if somebody gives us V1, they don't have to give us V2. You can figure it out. V1 equal V2. By the way, they don't give you these areas either. They don't give you these areas. You don't need them. Okay? Is there any pressure forces on the left-hand side of momentum? No, there's no pressure forces. Which way do we assume the force is acting on this support right here? To the left, minus. Minus. How about the right side? Okay, here we go again. Go around the control surface until you find a point where fluid crosses the control surface. Stop and do what it says. Start here, go up here. Stop, fluid's entering. Okay, do what it says. We have rho, the velocity there, V dot A goes this way. If you want to memorize it, some people say, you know, stuff going out has a positive V dot A. Stuff coming in, negative. That's okay, that's fine. Okay, so in this case here, we have the velocity going to the right. The dot product's minus V1, A1. So we'll put 1 up right now. At 2, okay, keep going on the top. No fluid crosses, no fluid crosses, no fluid crosses. Start going this way. Stop, fluid crosses. Okay. Density there, rho, incompressible, same density. Velocity vector. In the x direction, it's a vector quantity. In the x direction, I want that component of velocity. That's 45 degrees, cosine 45. B2, cosine 45. Which way is it pointing? To the right, positive. This guy here coming in, going out, negative. This guy here going to the right, positive. V dot A, cosine 0, plus 1. V2, A2. Rho, A, and V. Q1. Rho, A, and V. This is not Q1, it's M dot 1. M dot 2. Continuity. Write these guys down. Look at it before you work a problem on this, because they'll give you major hints. Oh, M dot 1 equal M dot 2. Okay. Equal M dot. Where is that M dot? I don't care. Take it at 1, take it at 2. It's the same thing. Continuity. Okay, this guy here then is V. There's M dot. V times, we have cosine 45 minus 1. Is that right? V, this is V1. V1 is that guy, and V2 is that guy. Yeah. Mm-hmm. So if you want to, better this way, go this way, minus M dot V cosine 1 minus cosine 45. Get rid of those minus signs, minus sign left, minus sign right. The force F is equal to M dot V times 1 minus cosine 45. Okay, so again, we looked at Bernoulli's, we looked at continuity, and we put them together with our momentum equation. Okay, a little modification of that is if we now look at a pipe fitting. Let's leave that up there. All right, here is a bigger pipe going into a smaller pipe. Okay. the flow comes in here, Q is given. The flow goes out here. This is 60 degrees. There has to be a resultant force, FR, here to hold us in place. And let's see what else we know. Is it water? I think it's water. Yeah, it's water. Water. Here's my control surface. Control volume. Okay. This is going to be P1. It's not, it's in a pipe. This is in a pipe. This is a pipe fitting. And this pressure in the pipe here is a P2. So neither P1 or P2 is zero. It's not leaving the pipe going out to the atmosphere. This is just a particular pipe fitting installed in the pipe network somewhere. Okay, we're going to assume our typical assumptions: steady state, incompressible, inviscid, along a streamline. So we have all the equations we need: continuity, Bernoulli, and momentum. Okay, let's, I'm going to get rid of continuity now. We've seen that enough. Okay. In my corner system, I'm going to write momentum in the x direction. Okay, so FR x direction, it's going to be in my picture minus pressure is to the right, P1, A1. Pressure here, the component in the x direction, cosine of 60, P2, A2, minus okay, and that's equal to rho V1, A1, V2 cosine 60 minus V1. I simplified it. We just did it on the board a minute ago. At location 1, the velocity is to the right, positive. But the dot product is negative. That's on the left. On the right, velocity is to the right, positive. The dot product is positive. Positive times positive, positive, plus B2 cosine 60. Okay. Let's see. What do we know? We have to know some pressures. We do. A1, P1. A1, 1 square foot. 25 PSI. Okay, at location 2, A2, a half a square foot. And the pressure, 23.6. Okay, and let's see what else we know here. I think that's all. It's incompressible. So we know that V1, A1 equal V2A2. Okay, so from all that, I'm not going to put all these numbers in here. You can just go through it yourself to make sure that you get these things right. The force in the X direction comes out to be 2750 pounds force.
Are we given V1?
Which one?
V1?
Z1?
No, V, the velocity that it's entering.
Oh, yeah, I'm sorry. Yeah. Thanks. Give it to you. Okay, so how do you, is Q1 equal to Q2? Yeah, I just told you up there. How do you get V1? V1 equal Q1 divided by A1. Got it. How do you get V2? Try Bernoulli's. Okay, got it. Put V2 in here, Bernoulli's. V1, Q equal A times V. What's V1, A1? Right there, 8. What's P1? Right there. What's P2? Right there. Everything's given, or you can solve it from continuity and Bernoulli's. Momentum in the Y direction. Okay, there's a Y component here. It's pointing vertically up. So FR plus, FRY. There's no pressure force in the Y direction at 1, but there is a pressure force in the Y direction at 2, sine 60. He was cosine 60. He's pointing upward, positive. P2, A2, sine 60. Okay, equal. There is no momentum at 1. It's in the X direction. Okay, it's gone. There is momentum here. Okay. It looks like this guy right here. Okay. We have rho. And we have, just like our V1, A1, we have V2, A2. And then rather than cosine 60, it's sine 60. The component velocity in the Y direction is sine of 60, V2 sine of 60. Do you know that guy? Of course you do. It's given you right here. It's 8. It's 8. Q1 equal Q2 equal V1 A1. Yeah, you know it. Equal V2 A2. V2, do I know it? Yeah, I solved for it from Bernoulli's. Bernoulli's. I know V1, I know P1, I know P2. There's P1. I got it. You got it. So put the numbers in there. 1685 pounds force. Upward. Now I want the total resultant force, FR, the square root of the sum of the squares. That is 3226 pounds force. The angle to the X at theta, tangent, arc tangent, the Y component 1685, divided by the X component 2750. So that guy is equal to 31.5 degrees. So here it is, 31.5 degrees, and FR is 3226 pounds. That's the result force, yeah.
Should the P2, E2 sine 60 for the momentum in the Y direction be negative?
P2, this guy here?
Yeah.
Okay. Yeah, he should be negative, thank you, he should, thank you so much. Yeah, he should. Right, okay, so you have one for homework like that, so, again, think permanently, think continuity, and then typically things work out for you a lot easier. Okay, we'll do one more. These problems I worked in class, plus the worked examples in the textbook, that should give you pretty good library of stuff to go ahead and do the homework for momentum. Okay, so this one looks like this. Stuff comes in here, stuff goes out here. Again, this is a pipe fitting like that, so it's not, there's no atmospheric component anywhere. This one is P1. Let's put our dash lines. This one is P1, and this is V1, and this is also A1. And leaving here, this is V2, A2, P2, and our control surface surrounds this fitting. You know, let me just say, that was a good point. Sometimes I do this. You know, over here, when I did this problem, and I had this plus sign here, there's a good lesson there. And here's the lesson. If you're doing this on exam when you're under stress, and you try and do everything in one picture, you can get confused. I don't like to do it in one picture, but people don't always like to draw enough drawings. Here's the way you should do it. This shows the fluid velocity picture. It really helps if you do another one like this. And this one, you show boy, there's no confusion there. I guarantee you, if you're taking an exam and you're under stress and you're trying to do too much on one figure, you run the risk of making a mistake like I made. I don't like doing it the way I did it because of just for that reason. This picture, well, let's start over here. This picture is the left-hand side of momentum, the summation of the forces. That's the left-hand side picture. This is the right-hand side picture. This is the velocities, the change in momentum. If you do this both ways, you'll reduce the risk of making a silly mistake like I made by trying to do it all in one picture. You see why? If I see that V2 arrow and I'm rushing through something with time constraint, I'm liable to say that P2 is positive. Oh, no, it's not. This picture clearly shows that it's not. So it really helps on exam to draw both those pictures. You can say, oh, I've saved time. You can save time, but you might make a mistake. Yeah, it's a time to save time. That's not it. It's better to draw two pictures. One is the left-hand side of the equation, and one is the right-hand side. And you won't make a sign mistake if you know how to take the dot product. Okay. All right, let's go over here now. This one here, let's look at this. I'll do what I said here, okay? So I've got this guy here, and like this, and like this. And this is a big one, and this gets smaller. So again, here's my pressure here. This is my P2. Here's my pressure here. This is P1. This is my force here, FRX and FRY. That's the left-hand side of momentum. Here's the right-hand side of momentum. V1, A1, V2, A2 vector. Okay, left-hand side. By the way, what's the force required to hold this fitting in place? Okay, left-hand side. FRX is minus. Pressure to the right. Pressure to the right. Equal the right-hand side. Now go over this picture over here now. Density is constant, incompressible. Steady state, yeah. Neglect friction, yeah. Okay. If I'm given V1, I can find V2 Bernoulli's. Again, they'll either say neglect the vertical change in elevation, or this thing's on a horizontal plane, which means it's on the ground. So they'll either say that Z1 equals Z2. They'll say neglect the change in elevation, or they'll say the fitting is in a horizontal plane, which means on the ground or hung from the ceiling, whatever it might be. Okay, rho times the velocity in the x direction, V1. I'll give this thing an angle too. Rho V1. V1 is pointing to the right. Positive. V dot A, negative. When you make your control surface, try and cut this where it's perpendicular to the velocity vector. Like down here. Okay, that's all for that one. Where it leaves the velocity in the x direction. Uh-oh, it's negative now. Rho plus rho. X direction velocity minus V2 cosine of theta. Okay. V2 cosine theta. Dot product V2 A2 cosine of 0 plus 1 plus V2 A2. Each one is a sign. Minus plus, minus plus. FRX equal rho V1 A1 times, this is rho V1 A1. We have another V1 in here. And then we have another V over here, V cosine theta is equal to rho V1 A1 V, this is V1 here, and this is V2. Okay. We can't put V outside of there, leave it like that. Until you do Bernoulli's, I'm not going to do Bernoulli's now. Do Bernoulli's relate V1 and V2. But what I want to point out is, here's parentheses, plus sign, minus sign. In the parentheses, plus sign. Don't memorize something and say, it's always plus and minus, because it's not. The minus here, plus here. Plus here, plus here. It depends on which way those velocity vectors are pointing.
On the left side of the equation, at the very top, the negative FRX plus P1A1 plus P2A2, does there need to be the angle involved for P2A2?
P2, yeah, there sure does again, thanks, I'm missing my angle there. So that would be we want the horizontal component, over here. So we want this guy right here. The cosine, right? Thanks, yeah. Good.
P2.
Oh, yeah, I've got a lot more terms here. Don't make that equal that. No. A lot of terms on there. Yeah, bookkeeping is critically important in this. Most people make their mistake in the signs, the pluses and minuses. That's where most people make their mistake. And don't memorize something because you're liable to be wrong because here's a plus minus, there's a plus plus, it really is a minus minus up here. Okay. That should be a minus. Minus, okay. So yeah, be careful on your bookkeeping. Remember continuity, remember Bernoulli's when you're solving momentum problems. Okay, so these should be enough for you to make a good dent in your homework. Okay, now, just so you know the agenda, next time we're going to do some homework now. I passed back. We're going to start energy. In chapter 5, there's 3 important equations. Continuity, momentum, and energy. So on Wednesday, we start energy. As I mentioned, the next midterm we'll go through chapter 5 and stop there at energy. Okay, this homework over here, I'll pick it up, all right? Anybody didn't get their homework, we're going to go over it, so. Okay. Let's take a look at homework and see. That's chapter 4. Yeah.
Oh, question?
Mm-hmm.
So back to the y direction, when you change it back to positive, isn't it the P2 still going downwards though?
Which
So
one now?
A moment in the y direction.
Oh, P2.
It's downwards, isn't it?
Yeah. Did I have that?
You had a negative before and then you changed it back to positive.
I think you're just using that as an example.
Yeah,
Like,
yeah, I must have been, yeah.
where I
No,
had
no,
it.
check your notes, make sure that, yeah, look at the picture up here, okay? Yeah, that's in the Y direction. By the way, we didn't do Y direction here. It's simpler, of course, because there's nothing here. I'm not gonna do the Y direction here. You could do it just like this. The only component is up here, the sine of theta. So you can do that yourself. All right, let's see. If you have problems with 4-4, 4-5, 4-8, see me after class and we'll go through it real quick. But I think most people would get those right. I graded for 24 and 36. Don't worry about 424 part B. It is not clearly stated. It is not easy to see. It is not worthwhile spending time on. It's not a good problem. So ignore part B. Problem 36. Most people got everything right, so I'm not going to go over that in class. 468. I want to go to 468. Let's put that right here. Okay. This is flow going down a wall. 468. Here's the wall. We have flow going down the wall. The velocity profile looks something like this. Okay. And let's see what else we know about that. Let me, 68. Yeah. It's actually a plate, it's not a wall, but we'll call it a wall, it's fine. This is the y velocity, so it's v. This velocity at this point is v naught. We're measuring x from here. I think that's all. And we know that this distance is called h. The width is b. When they say the width, they mean the dimension into the blackboard, the whiteboard, perpendicular. So it's b into the whiteboard this way. H is measured away from the wall. Let's see. Oh, he says that the velocity, they found out that the velocity, it's oil. We found out that the velocity is v naught over h squared. Times 2hx minus x squared. Okay. V naught and H are constants, okay. Show that the fluid sticks to the plate. What do you mean by there? He says sticks to the plate. Is the plate moving? No. When the fluid sticks to the plate, if the plate's not moving, the fluid's not moving. So show what? The velocity is 0 when x equals 0. Well, of course it is. Yeah, 0, 0, V is 0. That's easy. But just what the wording means when he says, show the fluid sticks to the plate. Part B, determine the flow rate across the surface AB. Oh wait, did I finish? Oh, and also show part A. Also show the shear stress at the edge of the layer, x equal h is 0, the shear stress. Okay, we might as well review chapter 1. Tau equal mu dv dx. And where is the edge of it? X equal h. Okay, so we're reviewing chapter 1, definition of viscosity mu, shear stress in a fluid. Okay, got to take dv dx. So dv dx, v naught over h squared, 2h minus 2x. Okay, now do what it says. Evaluate this at x equal h. So tau is 0. Okay. You could find the shear stress somewhere else. How about halfway when x equal h over 2? Not a problem. Just put in here x equal h over 2 and find the shear stress there. You can find the shear stress at the wall. Put in h equal x equals 0 at the wall. X equals 0. V naught over h squared times 2h multiplied by mu. That gives you the shear stress. Where? At the wall. You can find the shear stress anywhere from x equals 0 to x equal h. Okay, just by doing that. But do it in the right order. Don't put x equal h in here first and then differentiate. No, differentiate first and then replace x with h. Okay, that's part A. Part B, find the flow rate across the surface AB. And he's got a surface AB here. AB. It's a surface like this. Don't forget the wall comes out towards you. The fluid's flowing down the wall. So the flow rate Q equal V times A, but it has to be done correctly. V times A. That's the flow rate. It has to be an integral. Why? Because V is a function of X. Okay. We take a small differential here, and we call that dx. So what's the area dA? The area A is B times dx. Differential area coming out of the blackboard toward you. It's a strip. It's a strip. A differential strip. And we integrate that from x equals 0 to x equal h. V. Integral. Okay, put the v in there, this part of the v in there. Multiply by dA. dA. Integrate from x equals 0 to x equal h. B comes outside the integral sign. V naught's a constant, stays there. Go ahead and integrate. You've got an x squared over 2, x cubed divided by 3. Put x equal h, put x equals 0, solve it. It's simple, of course. and there's the answer. But part B was where some people have difficulty. How do you draw that little differential strip BDX? And why do you say BDX? Because it's a differential strip that comes out of the blackboard towards you. It's a strip. How wide is it? B, from my finger to finger. This is B. And how about this dimension right here? DX. Okay. And go from this side A to that side B, integrating it. Okay, any questions on that one? And yeah.
For the second part of part A, where it's asking
Yeah.
about the shear,
Right.
could you show that the velocity at x equals h, that all the h's cancel out and then v just equals v
Which
naught?
one is that right here? No, yeah.
Yeah, that's what I'm
Now,
talking about.
what step then?
But instead of using tau, I input x equals h into the velocity equation,
Okay.
and where all the h's canceled out and
Okay.
v equals v naught.
Okay.
Based on that understanding that there's no resistance, can you conclude the same thing or no?
Probably not, no.
No.
Why? Because you solve for V naught. But if you put x equal h, okay, you're gonna get, well, what's this gonna be? 2x squared minus x squared? So x squared, and put that equal to h, then v is V naught.
Yeah.
You've proven that that arrow is correctly labeled V naught.
Oh,
Now prove that the shear stress is 0.
okay.
Okay. Okay, the last one we'll do is, I'll give you a couple of hints on I think it's 46, yeah, or 46. Okay, 446. Let's see what it says. A fluid flows past a sphere. Okay, there's the sphere. Upstream velocity 40 meters per second, V naught. 40 meters per second. From more advanced theory, it can be shown that the velocity on the front part of the sphere is V equal 3/2 V naught sine theta. Theta is the angle from here to here. And that velocity is tangential. That's V. Advanced theory says show that to be true. Don't worry about proving that from advanced theory. Determine the streamwise and normal components of the acceleration at point A, given the radius of the sphere. So this radius, we call it R naught, radius of the sphere, of the outside. Okay. A normal, V squared over R, and A along the streamline, A sub S, V partial V with respect to S. R is R naught. And you can find V there. You know what theta was given. Theta was 40 degrees. You know V naught. V naught was given. It was 40 meters per second. So I know V naught, I know theta, I can find V. I put V in here, I square it. I divide it by R naught. I know R naught. R naught is 0.2 meters. Okay, so now I've got the normal acceleration this way, normal to the streamline. Now I do the second one. The second one, this guy, I know V, I just told you how to find V. Now we've got our dVds. dVds is partial V with respect to theta. times partial of theta with respect to s, chain rule. Why do I do that? Because I'm given velocity as a function of what? Theta. I want theta in there somewhere. This is the velocity partial with respect to s. No, I don't see s up here. What do I see? I see theta. So I make it dv d theta. Can I find that? Well, of course I can. Cosine of theta. Partial is with respect to theta. Cosine of theta. I can find that. I've got it. D theta ds. Now I go back to my geometry. Let's see, an arc length on a circle, that's s. That's the radius times the angle theta. Okay, there it is. Do what it says. Solve this guy for theta. Theta equal s over r. And this is constant, r naught. Constant. Take the partial of theta with respect to s. 1 over r naught. Got it. That goes in here. I know it. Take these two guys, multiply them together, multiply it by b. There's b, and there's the answer for as. But you need two things, chain rule, and how is s defined in terms of theta on that picture. Those are the two things you need to solve. Okay, good stopping points. So we're going to start on the energy equation on Wednesday. So no homework due Wednesday. Next.